This is the IEEE Computer Society Distinguished Lecturer Webinar Series brought to you by the Distinguished Visitors Program. The Distinguished Visitors Program delivers tools for individuals at all stages of their professional careers through visits to chapters, offering opportunities for individual interactions, and to the membership through webinars by respected professionals. We have distinguished visitors around the world who cover machine learning, cybersecurity, robotics, big data, cloud computing, blockchain, and cryptography, among others. Chapters can request a distinguished visitor on computer.org/distinguished-visitors. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program. Welcome to our Distinguished Lecturer Webinar Series. My name is Kerry Cosby, and I'm the Chapters Manager at the IEEE Computer Society. I oversee our more than 500 chapters, professional and student chapters around the world, and manage our Distinguished Visitors Program. I'd like to take care of some housekeeping tasks. You can ask your questions in the Q&A panel. Dr. Tripathi will answer as many questions as he can following the presentation. When you're writing your questions, if it relates to a particular slide, please do your best to reference that slide. The webinar is being recorded, and the recording will be made available after the webinar. Today's discussion is consensus protocols in blockchain systems. I'd like to introduce our speaker. Anand Tripathi is a professor of computer science at the University of Minnesota, Minneapolis. He's a fellow of IEEE. He received his PhD in electrical engineering from the University of Texas at Austin in 1980 and a BTech in electrical engineering from the Indian Institute of Technology in Bombay in 1972. From 1981 to 1984, he was the senior principal research scientist at Honeywell Computer Science Center in Minneapolis. During 1995 to 1997, he served as program director at the National Science Foundation. His research interests are in distributed systems, middleware frameworks, system security, and fault-tolerant computing. Dr. Tripathi, I'd like to pass the floor to you.
Thank you very much for inviting me for this webinar. And I would like to also thank all the participants for coming here for this webinar. So in today's webinar, I will be presenting models and protocols developed for consensus protocols and blockchain systems, and we'll start with the origin of the blockchain paradigm in Bitcoin. So my presentation is structured as follows. I will spend about 15 minutes, present an overview of blockchain paradigm, its development in Bitcoin, and its consensus model, which is based on the notion of proof of work. It is also called Nakamoto consensus. There are several limitations. There are also drawbacks of this model, and one important thing is energy footprint, enormous energy footprint of this model. So several alternate models for consensus and blockchain systems have been developed in recent years. So we are going to look at some of the most important significant developments over the recent years. One approach which has been is use of classical consensus protocols, such as crash or Byzantine Fault Tolerance protocols. And there's a very long history, more than 30 years of history, close to 40 years of development of fault-tolerant protocols based on crash of Byzantine faults. So one exploration has been that how to adopt these protocols, utilize these protocols in blockchain systems. Other thread of investigations and developments which has taken place is alternate approaches to proof of work. These are called proof of X models, and X can be many different things. Proof of stake is one very commonly adopted and investigated today. Proof of authority, proof of activity, proof of elapsed time, and we can go on like proof of burn and proof of space. So there are many different models. We are going to look at some of the important ones. There's a completely different approach some systems have taken is instead of having a linear chain model for blockchain, it's using a directed acyclic graph structure for maintaining the records and the information of transactions. Finally, conclusions and question answer session for 5 to 10 minutes. My presentation may go for about 60 minutes kind of duration. So origin of blockchain model, it started with Satoshi Nakamoto's very famous paper now, Bitcoin, this peer-to-peer electronic cash system, which was published in October 2008. And the Bitcoin system became operational in January 2009. So what is Bitcoin? It's based on peer-to-peer computing model in an open environment. There is no centralized control or authority and no trusted third party is needed. It's an open permissionless system. Any user can participate, download the Bitcoin software, and connect to the Bitcoin network. It's a dynamic network. So typically the size tends to be around 10,000 full nodes. Currently, the blockchain requires about 347 gigabytes of storage. So the full nodes essentially maintain the entire state of the blockchain. It's worth noting here that besides creating the most popular cryptocurrency, there's Bitcoin made some two important truly novel contributions. One is the development of blockchain paradigm. And the second is solving the consensus problem in a very large dynamic network of participants which are of unknown credentials. So these are two significant contributions which Bitcoin make, and that is the focus of today's talk, blockchain and consensus problem. So what's a transaction in the Bitcoin model? It's a very simple notion. It's a transfer of ownership. So one who is owning some coins is essentially transferring those coins to some other users. So the current owner transfers ownership to some other users. So that's a model of ownership transfer for Bitcoins. So the purpose of blockchain and the Bitcoin system is essentially to prevent double spending attacks and also to ensure finality of transaction confirmation. When should we determine that this transaction is now confirmed and final? So what's blockchain? It is nothing but a ledger which is maintaining a serial history of acceptance of transactions in the system. So the transactions are ordered in this serial history, and all nodes in the system should have the same view of this serial history in order to prevent the double spending attack. So Bitcoin's blockchain, it is a replicated ledger. It is stored at all nodes, all full nodes. In case of Bitcoin, it is stored at 10,000 nodes. It is also an append-only ledger. Only the records are appended to it. It's also the records are immutable. So once appended, they cannot be removed. And a record in the blockchain cannot be altered or modified. So these are the characteristics, properties of a typical blockchain. Now, Bitcoin's blockchain essentially is a linked list of blocks, and each block contains a set of validated transactions. There are some nodes in the system which are called miners, and they play a very special role in maintaining the operational health of the system and operation of the system. And the role of the miner is to collect a set of transactions submitted by the users, collect them, validate them, put them in a block, and then propose that block as the next valid extension for the blockchain. So for this task, the miners are incentivized in terms of transaction fee, which is paid by the user. The miners are also create or mint new coins in the process of proposing a block. If the proposed block gets accepted, finally becomes the part of the blockchain, then the miner will be getting reward of some number of coins in the system. So with these incentives, the miners are eager to work and create new blocks in the system. Miners compete to create blocks, new blocks. Multiple miners may concurrently propose different blocks. And here is the crux of the problem, the fundamental problem. Only one of the concurrently proposed blocks should be finally accepted as the valid extension to the blockchain. And that is the fundamental consensus problem, which requires a consensus protocol for accepting only one of these proposed blocks in the system. And that requires the agreement of all nodes. All nodes would agree that this is the valid extension, next extension of the blockchain. Now, Bitcoin's consensus model, which is now called Nakamoto consensus model, it solves this problem, the consensus problem, in a probabilistic manner. In the sense that if more than 50% power, computing power, is with honest players in the system, then eventually this blockchain paradigm, this will lead to consensus on the ordering of the blocks appended to the chain. And Bitcoin solves this problem with a mechanism called proof of work. So proof of work is nothing but a miner has to do some work. It solves a computationally hard crypto puzzle. So a miner has, in order to propose a block, a validated block, miner has to do some additional work solving the crypto puzzle. The crypto puzzle is such that it is difficult to solve, but its solution can be verified very easily by any node in the system. And also the chances of solving this crypto puzzle is random, but at the same time, it is also, it's a computationally, it's a hard problem. And chances of solving is proportional to the computing power which the miner possesses. Now, the chances of winning, there's a difficulty level is set, and the one who wins this computation that solves the crypto puzzle quickly has the best chance of proposing a block and getting its block accepted in the chain and get the rewards in turn. So the proof of work model is designed such that, or is it designed for one motivation, to keep the transaction confirmation irreversible. So once a transaction is confirmed, it should not be possible to reverse that transaction, and we'll see that shortly now. So this is the structure of Bitcoin's blockchain. It's a schematized here, simplified here. Each block contains a link or a pointer to the previous block, and this link and pointer is in terms of the hash value of the previous block's header. By embedding in a block the hash value of the previous block, that serves as a link, a pointer to a unique block in the blockchain. It also contains the digested hash value of all the transactions in the block, that is called the Merkle root. It also contains a nonce, which is a random number, and this nonce plays a central role in the proof of work crypto puzzle, and we are going to see that now. So the miner's job is to validate a set of transactions, put them in a block, create the block header. In the block header, include the hash value of the previous block's header as a link, which serves as a link. Also add the Merkle root of the transactions in its block. Then select a nonce, a random number, and apply the hash SHA-256 hash 2 times. It will result in a computed hash value. And the puzzle is, this hard crypto puzzle is that the computed hash value should be below some target value. And the target value is essentially set such that the k leading bits, the k most significant bits of the hash value should be 0. And the k is adjusted. That's a difficulty level, and that's adjusted periodically. So once a miner has been successful in solving this crypto puzzle, that finding the hash value which is below the target level, the miner is successful in mining a block. The miner would publish that block over the network, P2P network. So it can happen that multiple miners are successful in mining a block on top of the current last block, and they propose this as a valid extension for the blockchain. So the picture may emerge like this. On top of block B, one miner proposes block C, another miner proposes block D. Some people who have seen, miners have seen C, continue mining on top of C, and that branch extends. Some other miners may extend branch D. So what we see here, that rather than a linear chain, this is essentially resulting in a tree-like structure. Many branches are getting created. For example, we call it a fork. At node B, 2 branches are forked, one starting with C, one starting with D. So the question arises, which branch should be considered as a valid extension of the blockchain from A, B? Should it be D, or from A, B, should it be C? So the rule adopted in Bitcoin is very simple. It is called the fork choice rule. And this rule says that a node should always accept the longest chain as the valid one and abandon the other branches. So a miner would always mine on the top of the currently known longest chain in the system. If miner is currently mining on one branch and another branch becomes longer, then essentially the miner would switch to that branch. So abandoned branches essentially contain blocks or transactions which are not accepted in the system, which these transactions will have to be resubmitted. And they essentially have to be included in some other new blocks mined by the miners. So this means that some validated transactions which were present in some blocks may get discarded, and we call it, these are called reverse. The transaction got reversed. Now, this is the model for, and that is the Nakamoto consensus model. And this model assures that if the 50% of the computing power is with honest players in the system, then eventually, then all nodes will agree on a common prefix of sequence of blocks in the longest chain, starting from the first block, which is called the Genesis block. Now, Bitcoin's performance, the difficulty level of crypto puzzle is periodically adjusted to keep the rate of block generation every 10 minutes. A higher rate would result in higher probability of forks, and the fork means it can essentially, it's a wasted computing power. Bitcoin also limits the block size to 2 megabyte. Earlier, initially it started with 1 megabyte, and it was later on, it was increased to 2 megabyte. Currently, it tends to be about 1.3 megabytes. A typical transaction size is about 150 to 250 bytes, and a typical block contains somewhere 2,000 to 4,000 transactions. So all these, the settings of these limits, these settings limit the transaction processing rate in Bitcoin to about 7 transactions per second. That's the kind of a limit with these settings arises. So another problem with forks is the double spending attack. So here's a scenario. Alice has some business transaction or deal with Bob, and she needs to pay some coins which Alice owns to Bob. So she creates a transaction, Alice to Bob payment, transfer of ownership of her coins to Bob, and she creates this transaction. And this transaction got included in a block C. She sent another transaction. This is called double spending. Same coins, Alice transfers to herself and sends to another miner, and that gets included in block D. Now we see here are 2 branches. One contains Alice to Bob transaction, other contains Alice to Alice transaction. Now it so happens in this picture here that the branch starting with D, that branch gets longer, and that will be accepted as a valid extension or the chain or the longest chain in the blockchain, and the branch starting with C will be abandoned. Essentially, the transaction that is Alice to Bob ownership transfer, coin ownership transfer, that is reversed, that is discarded. So the question arises, how to ascertain the finality of a transaction? For this, Bitcoin, the model is, the heuristic is very simple. A transaction is considered irreversible if 6 additional new blocks have been appended to the chain after its block. When that happens, there's a highly diminished probability that another branch will become longer and this transaction will get reversed. So that is the heuristics typically used in ascertaining the irreversibility of a transaction. So this means that given that it takes 10 minutes to generate a block, 6 blocks will take about 60 minutes. It takes 50 to 60 minutes kind of time for ascertaining the confirmation of a transaction. And this makes Bitcoin unsuitable for quick point of sale kind of transactions. Let's look at the energy footprint of Bitcoin. There's a very useful site, Cambridge Bitcoin Electricity Consumption Index, which you can see at that site. And every 24 hours, it assesses the energy footprint of Bitcoin. And this is a snapshot on June 7th this month. And it was showing that Bitcoin's annual consumption was 116 terawatt hour estimated on that day. It was 116 terawatt hour. And that gives us the mining one block. It takes 2.2 gigawatt hour of energy. And creating or minting a new Bitcoin is taking 350 megawatt hour of energy. And if you assume that there are 4,000 transactions in a block, then per that day of snapshot, and this keeps on fluctuating and changing, but you can find that site also gives the average values over some extended period. So all these drawbacks, limitations, energy footprint, they have motivated researchers of blockchain technologies to essentially investigate other alternate models. Motivation is obviously reduce energy consumption footprint, increase performance in terms of transactions, number of transactions per second, increase transaction confirmation latency, which is several minutes in blockchain, to bring it down to few seconds kind of level, and aim for deterministic finality of transactions. So here we see several alternate approaches, several balloons here, and the bigger ones I'm showing here, the more significant approaches. So classical consensus protocols, that's a significant approach, and there have been many adoptions and integration of classical consensus protocol, and I'm using the umbrella term BFT, stands for Byzantine Fault Tolerance protocol, for such protocols integration in blockchain technology for consensus problem. Other is proof of stake model and proof of authority, proof of elapsed time, proof of distributed proof of stake model, proof of space time. There are several such proof of X models are there. And we are going to look at, it's not possible to go over all of those, but we are going to look at some of the significant ones here. So I'm going to talk about classical consensus protocol, which is a history of more than 30 years, use of classical consensus protocol like Byzantine Fault Tolerance protocol for consensus finality, and typically it is combined with proof of work or proof of stake or proof of authority, some other models. And you will see this pattern that they are not complete, they are not mutually exclusive. Some of these in the hybrid designs, these are integrated together, various models. Proof of stake. And the motivation here is that those who are holding stake in the system are most inclined or most likely to be inclined to keep the health of the system and its operations healthy and working. So such users or participants who are stake in the system, they are interested with the job of performing validation and consensus in the system. And again, the motivation, avoid energy consumption of proof of work. Proof of authority, that those participants who are of known credentials and trust level, they can be assigned for performing validation and consensus tasks. Proof of elapsed time is development from Intel, and it requires trusted execution, hardware level execution facility in the processor. And I will be talking about all these. And finally, directed acyclic graph, that essentially abandon the linear structure of the blockchain and adopt a directed acyclic graph structure for either blocks or the transactions in the system. Now, all these investigations of various approaches and their adoption have been essentially centered around two broad classes of blockchain models, which is the permissionless blockchain or the permission blockchain. Permissionless model is Bitcoin's model, also adopted in Ethereum. It's an open model. There's no restriction on or control on the participation of users. These are also called public blockchains. Any user can join the system using their pseudonymous identities. Their real-world identities and credentials are unknown. Such environments are open, so they are also vulnerable to various kinds of attacks. Participants may be malicious, participants may be selfish, they may be dishonest, they may also acquire multiple identities. And these multiple identities, this problem is referred to as Sybil identities or Sybil attacks. In contrast, the permission model of participants, their admission in the system is controlled. It is controlled based on their known credential, their trust levels, or reputation. There is no underlying cryptocurrency associated with these models, and these are suitable for operations within an organization or across different organizations in a consortium. So these are also called the private blockchains. Now, here's a very brief overview of consensus protocols and distributed systems. All these protocols have been developed in the context of building fault-tolerant systems. Fault-tolerant or resilient services. Typically, a service is implemented as a collection or a group of processes which work in virtual synchrony, performing the same steps of operation. So the models considered in the development of classical consensus protocols have dependent on the process failure model and network synchrony model. Let's look at the two process failure models which are commonly considered. One is a crash failure model. In the crash failure model, a crash process essentially becomes silent. It does not execute any action. It doesn't perform any operations. In contrast, a Byzantine failure model, a process can still keep on executing operation, and possibly it can perform malicious operations, intentionally trying to disrupt the normal operations if the process has been taken over by an adversary. There are two basic requirements which are needed to be addressed, the properties which a consensus protocol should have. One is the safety property. Then this requirement is that all correct processes should adopt the same agreement decision. That's the correctness of the protocol. And other is a liveness or termination property, that the protocol terminates with an agreement decision. Now, there are two different threads of liveness property, and one is a deterministic termination model where every correct process makes the agreement decision in after some finite bounded number of communication rounds. Compared to that, the probabilistic model says that a correct process does not make an agreement decision, that probability approaches. The probability the correct process doesn't make decision that approaches zero as the number of rounds in the system increase. Several consensus protocols have been developed in the past. It's a long history. So typical models are either crash failure models based on crash failure models or Byzantine failure models. Under the crash failure models, given n processes or process replicas, and out of which m may be faulty, m members of the group may be faulty. The protocols developed have been like view-stemmed replication, Paxos, and Raft. And Raft is currently one of the most widely used library under this model. And this model requires that majority of processes should be correct. So under the Byzantine failure model requires that 2/3 of the processes in the system should be correct. That is, the supermajority of processes should be in the correct. In the context of Byzantine failure model, the very first protocol developed was Practical Byzantine Fault Tolerance Protocol by Castro and Liskov, PBFT. Then have been subsequently many other protocols have been developed, refining or improving on various aspects of this protocol. Now, here is something very important to note, that most of these protocols have a leader-based execution model. So essentially, one of the members in the group acts as a leader and proposes the next value for the decision or the next operation to be performed. And the other members in the group essentially do the voting, and finally certain rounds of voting, then the agreement is reached. Now, such models are susceptible to leader failure. A leader may fail, and in case of leader failure, then it requires, of course, there's a failure detection protocol is required, and a reconfiguration protocol or a leader election protocol is required. So such protocols are called the view change protocols. Essentially, they change the group membership and the leadership in the group. So these are called the view change protocol, and that's one of the most difficult aspects of such consensus protocols. It's also called the epicenter of consensus protocol. The classical consensus protocols, their operating environment has been fairly limited and restricted. It's a fixed size group of processes participating in the protocol, and the processes are from known credentials. Typically, the group sizes tend to be fairly small and 10 to 20 kind of range. So these protocols were developed in this kind of range. More recently, there have been a number of developments that protocols using some threshold cryptographic kind of techniques, they have extended to 100 to 200 kind of range of groups. Now here's a comparison of use of proof of work model, which is coming from Bitcoin, to the BFT based model. The proof of work model is permissionless, BFT is permissioned because a group has to be formed, view change protocol, it is admission and the group is controlled. Proof of work is highly scalable, and that's pretty much demonstrated by the daily operations of Bitcoin up to 10,000 nodes. Typically in the BFT, the group size is limited to 20, and with some newer protocols, the techniques used there, crypto-based techniques, can go to 100, 200 kind of group size. The transaction processing rate of Bitcoin and proof of work model can be in range of 5 to 50 transactions, maybe 100 transactions per second, whereas classical consensus protocols can lead to much higher transaction rate, 1,000 to 5,000 kind of range. The latency in the confirmation of transactions, as we have seen in Bitcoin, is several minutes versus the latency in the BFT kind of consensus protocol. They will give about, few tenths of seconds latency. Now, coming to the finality of a transaction confirmation, the Bitcoin's model is probabilistic finality model, where the BFT gives deterministic finality of consensus. Finally, looking at the failure tolerance, the proof of work model can tolerate malicious participants, provided they control less than 50% of the computing power. In the BFT protocol, the threshold is a bit lower, that the malicious participant, provided they control less than 1/3 of the voting power, and I want to emphasize the voting power here, that control less than 1/3 of the voting power, then these protocols can tolerate such malicious players. Now, classical protocols in the context of permission system, their adoption, integration, and use is relatively straightforward. And because a permission system, the participants' credentials and trust levels are known, so the trusted participants can be assigned to the groups performing validation or performing consensus. In contrast, the permissionless systems, the problems, the challenges are truly unique and intriguing because large population of users of unknown credentials, dynamic population of users, there's a churn in the system, participants can come and go. And these problems have been addressed in several research systems, and I'm going to be talking about those shortly. Now, looking at the consensus protocols and permission system, which is a relatively somewhat, I would say, straightforward kind of integration here, that classical consensus protocols are naturally applicable in permission systems because of known trust levels. So the trusted participants can be assigned to groups responsible for validation or consensus. And these groups are, in current lecture, these are called committees. So I will use the word committee for the consensus group of participants performing, executing consensus protocol or validation. There are a number of libraries currently widely used. BFT Smart is a very widely used library for Byzantine Fault Tolerance. Raft is based on the Paxos model, that is the crash model, crash failure model. In that context, Raft is widely used. Yak is yet another consensus protocol, and Aura, Click, these have been used in Ethereum's test networks, Coven and Rinkeby. And there's also scalable Byzantine Fault Tolerance protocol from VMware, which has shown that these protocols can be extended to group sizes of about 200. So BFT and permission systems have been used in Hyperledger. Hyperledger is a family of independently developed open source permissioned blockchain platforms, and it's under Linux Foundation. So Hyperledger Fabric is from IBM, and it allows a pluggable option for either including BFT Smart Library or Raft, Hyperledger, Iroha, and several organizations, Seramitsu, Entity, Hitachi, Kolu, they are involved. And Soramotsu developed YAC, yet another consensus protocol. Intel's Hyperledger Sawtooth, and that allows options for several pluggable protocols. Initially, it was based on the POET model. POET is Proof-of-Elapsed Time. It also permits option to include a BFT protocol, a REF protocol. Then there are several other blockchain systems, and some significant I'm just mentioning here. R3 Corda, created by consortium of 9 financial organizations, and it allows integration of BFT Smart and Raft. There's a notion of notary service. A notary service is a collection of validators which can use BFT Smart and Raft, and there can be multiple notary services in the environment. Ripple and Stellar's model, it doesn't follow the traditional BFT protocol, the paradigm and the patterns. It's a very different kind of model. In Ripple, in the Ripple protocol, there's a cluster of validators, okay, and there can be several clusters of validator. It requires overlap, that any two clusters must have at least 40% overlap. And within the decision is made within a cluster to accept a transaction, and the acceptance requires 80% of vote in the cluster. Now, Stellar adopted initially the Ripple protocol, then it switched to Federated Byzantine Agreement protocol later on. Now, looking at the BFT-based consensus protocol in permissionless blockchain systems, and that's where there are several challenges. Because of open environment, unknown credentials of the users. So the question arises, number one, how to determine eligibility of participant to serve on the committee, because we want to have a BFT consensus committee, how to select the eligible participants. And typically for that, either proof of work or proof of stake is used, because such eligibility should be made Sybil resistant. So one should not be acquire large number of identities, and each identity would be then get one vote, and it has to be limited in proportion to their either computing power or stake. The second problem is selection of a subset from the pool of eligible participant. How to select or elect, okay, a subset of the eligible participant to serve on a committee. And typically several thousand participants may get selected from a pool of 1,000 or so. So, and the probability of a participant getting selected, it tends to be proportional to, or it is kept proportional to the computing power, if proof of work model is used, or with proportion to the stake currently that participant has. And that's based on proof of stake model. Now, open systems are also vulnerable to denial of service attacks. So many of the designs have required that the committee should be configured and changed frequently or periodically. Another requirement some designs have looked at is hiding the identities of the committee members and the leader, because otherwise the committee members or the leader may become the target of denial of service attacks. So we are going to look at some of these designs. And finally, number 4, the incentive model for participation. That's important. Participants have to be encouraged to participate and perform validation and agreement and consensus protocol execution. But at the same time, there has to be a penalty model for misbehavior. And that's important. And we'll see in just in a few minutes. So use of BFT protocol in permissionless system. The designs have been either based on integration of BFT with proof of work or integration of BFT with proof of stake. I'm going to present next integration of BFT with proof of work, the hybrid approaches. I'm going to talk about integration of BFT model with proof of stake later in the larger context of discussion of proof of stake. So looking at the hybrid model of BFT with proof of work. So proof of work model provides protection against Sybil attacks. So the participants have to do some proof of work, like solving a crypto puzzle, mining a block. The proof of work also acts as a oracle for leader election. So typical model is that the miners or the participant who mine a new block, they present this as a proof of their eligibility to the current committee and essentially drive a protocol for configuration or view change to integrate a new successful miner into the committee. And there are different models which have been adopted for changes in the committee membership. Either it can be a sliding window model or it can be a complete overall the committee. We'll see a couple of examples now. I'm going to talk about 2 or 3 examples. Peer census was the first system to adopt this kind of model, hybrid integration of BFT with proof of work. So what is the benefit of including BFT? It's consensus finality. It's a consensus finality. That way, the block generation rate, agreement on the block generation can be much higher, and then the throughput, the transaction throughput can be increased. And the transaction confirmation, the finality is guaranteed. So this coin is one example of integration of proof of work with BFT. So its model is the nodes will do the mining, the proof of work, and the one which a participant mines a block successfully, essentially propose that block to the current committee, and once it is accepted, the miner becomes the part of the committee, so the committee configuration changes, and the miner also becomes the new leader of the committee. So a view change protocol execution takes place. The committee membership in this coin changes gradually. So when a new miner, the one who successfully did the proof of work, becomes the committee member, the oldest member is removed from the committee. Bitcoin did some other things. It also used collective signing to reduce the message complexity and made the protocol, BFT protocol, more scalable. In most of these systems, the mining rewards are essentially shared by all committee members, and that is the incentive model. Solid design is very similar. Similar kind of model is used in the Solidar design, where the participant who is successful in mining or performing proof of work successfully essentially drive the view change protocol and become the new member in the committee. The model very much a system called Elastica, and it's a commercial system called Zilliqa is based on it, essentially use the same model of proof of work to determine the eligibility of participants to become the member of the BFT groups. What is novel about this system that it uses sharding, partitioning for higher throughput. So the transactions are sharded based on or sharding means partitioning and in different partitions or shards. And for each shard, there's a separate committee is for BFT or consensus protocol, and there's a one top level committee. So first the consensus or agreement is done by the shard level committee, and then it proposes that block for the global consensus to the global or the top level committee, which is called the consensus. What is interesting here is that the system operates in epochs, and every 24 hours, there's a complete reshuffling and reconfiguration of the committee. So every 24 hours, the participants have to do the proof of work again and establish their eligibility and identity to join the committee. And as a part of the proof of work, they would generate some hash value, and the least significant or lower significant S bits of the hash value, they will be used as the shard ID for that particular participant. So every epoch or 24 hours, the participants may join a completely different shard committee. Now let's look at the proof of stake model, which emerged as a fairly attractive alternative to the proof of work and fairly, I would say, very broadly being pursued and investigated and utilized today. This model is usually combined with other approaches such as BFT or proof of work and a hybrid approach. So let's look at the notions and the issues involved here. So the basis is that those who are holding stake in the system, they're most likely to be interested in maintaining the health of the system and the operations of the system. Now, because the stake represents a scarce resource, and it is difficult to obtain, just like proof of work kind of model. Anybody who's holding stake in the system can essentially participate and influence the operation, and that is the voting power, which will be proportional to their stake in the systems. Instead of mining, the term normally used in the context of proof of stake is either minting the blocks or the forging the blocks. So the stakeholders, they can participate in minting the blocks, forging the blocks, proposing the blocks, and also participating in consensus committee for essentially getting the ordering of the blocks. A model for reward and penalty is important in this context. Reward model is needed to encourage participation of the nodes. A penalty model is very important and very needed. It's also called the slashing model, and slashing model would result in loss of deposit, loss of some stake. And those who are essentially to prevent those who may cause intentional fork in the system, or some may cast conflicting votes in a voting scheme or consensus scheme, such participants need to be penalized or punished. So a penalty model is extremely important. Now, there are several different models for stake valuation. How do we determine the stake of a participant? The simplest model, number one, the simplest model is the current balance of coins in the system. Number two is the coin balance which has been stationary for some time in the system. So essentially, the participant is vested in the system for some period of time. For example, that is used in the next system. And the next system required that the stake which has been in the system for the last 1,440 blocks. So that stake, those coins will be only considered as the stake for the proof of stake based model execution. Other is the age of the coin in the system, and this was adopted in peer coin. Peer coin was the first proof of stake based system. So it is not the number of coins is one holding, but also the number of days one has been holding that coin. So coin multiplied by number of days. Now such a model encourages hoarding and holding of the coins. So that means the coins will not remain in circulation. But there's another downside, that someone with very small number of coins can hold it for a very long time and acquire disproportionately high influence in the system. For example, voting power. So for that reason, such model, coin age kind of model where the coin age can keep on increasing, is not attractive, and it has to be limited. So there is this model used in Redcoin, weighted coin average model. It is also called proof of stake velocity model. So the coin age does not keep on increasing linearly forever. The coin age model, it may increase linearly for some short time, like 5 days or 7 days, but after that, it will be sublinear growth and it will plateau at some point. So this model is designed to discourage hoarding and holding coins, and also to avoid the situation where someone with small coins can get disproportionately high influence. The fifth one is the most effective model, okay, and most attractive, most effective model, and that is the stakeholder has to lock some deposit, some bond, in order to participate in validation and ordering, and there has to be coupled with it a penalty model. Slashing of the deposit in case there's a misbehavior is detected and proven. One more thing, that the deposit or the bond is typically held for a long time. It cannot be released for several weeks or several months. There are several attacks models which have been discussed, and there's a reference I'm showing at the bottom of this slide. So there were One is called the nothing at stake model. If there's no penalty involved, then a stakeholder, for example, a participant who is forging block, can propose blocks on all branches of the tree because there's no penalty involved, and the attacker would essentially try to maximize essentially all the possibilities that whichever branch finally gets accepted, the attacker would still gain some reward. So this is called the nothing at stake problem. And the solution is very simple. There has to be a penalty structure needed. A more difficult problem is the long range attack. Somebody who was holding stake way back in the history of that blockchain, in fact, go back to the very early stages of blockchain, may not be having stake now in the system, but may go back to that and creating fork based on the stake they were holding at long time ago, and creating a new branch and start working on creating a new fork and branch in the system. An attacker may also buy old stake from others, or buy their signature keys or bribe them. So the solution for this is periodic checkpointing to guarantee the finality that such long-range attacks cannot be done. For example, the next system, proof-of-stake based system, essentially does every 720 blocks, it does the checkpointing. So fork cannot be done. Nobody calls a fork from any block preceding the checkpoint block. There are also other attacks called stake grinding attack. Most of the stake-based protocol use some randomized algorithms, random pseudo-random election algorithms, and they use the state of the blockchain, some of the hash values computed on the blockchain as a seed values for driving the election. Now, some nodes may do what is called the costless simulations. Before proposing a block, they may do costless simulation to manipulate or build a block such that the embedded hash values on those blocks will favor this particular participant in the future elections. So these are called the stake grinding attacks. And I've shown the reference here, give very useful discussions of these attacks. Now, the proof-of-stake based models. Proof-of-stake-based model, there are 4 paradigms. Proof-of-stake combined with proof-of-work. This is called the chain-based. Proof-of-work, proof-of-stake, essentially used for electing a committee of leaders, and the leaders would propose the block, take their turn and propose the block. There's the committee-based model. Then proof-of-stake combined with Byzantine Fault Tolerance protocol I mentioned earlier. Byzantine Fault Tolerance protocol earlier we saw combined with proof of work. Now we will see combined with proof of stake. Then there's a notion, the delegated stake model. So let's look at the hybrid proof of stake with proof of work model. It is still proof of work model, solving a crypto puzzle. But the difficulty level is modulated. It is reduced based on the stake level. So difficulty level for the miner reduces based on the current stake level, and forks are still possible. Longest chain rule is still required. Now Peercoin, which was the first proof of base system, adopted this model. It was also adopted in next model. Peercoin system used the coin age as the stake valuation. It also did something interesting and useful. It limits the hashing. It limits the attempts a miner makes every clock tick for doing the proof of work model. So a miner is limited to perform solving the crypto puzzle. It's limited to once per clock tick, because the crypto puzzle also includes the current clock tick or the time value in it. Committee-based models have been explored, investigated, and what I'm showing here, okay, Ouroboros and Snow White. I'm going to just briefly describe the Ouroboros model. The model is the following. The time is divided into epochs, and each epoch has n slots. For each n slots, n leaders will be elected prior to the epoch. And the way election is considered, is conducted among those stakeholders. First, a multi-party coin toss protocol is executed, and which will compute a random seed agreed upon by all the participants, stakeholders, and each one will then perform a pseudo-random election computation and determine the N leaders for the next epoch. And these are the committee of leaders. Each leader is assigned to one slot. In that slot, the leader would propose the next block in the system. Same random seed then used for electing the participants for the next epoch and so forth. Now, Ouroboros requires strong synchrony. If the strong synchrony gets disrupted, then it may happen that two participants or the committee members, committee of leaders may think it's their slot and they may propose. So the forks are possible. And the resolution is based on the longest chain rule. Ouroboros Preos, okay, it has some interesting aspect. The way the committee is elected, the election or the membership is kept private or secret only to the committee, the elected members of the committee. And the way it does is using verifiable random functions. So what's a very verifiable random function? The notion is very simple. This function takes an input. It also takes the secret key of the participant executing the function. It will produce an output. It will produce also a proof. Now, anyone can verify that proof provided they have access to the public key of that participant. They can verify that indeed this output was produced by this specific participant and using this specific input. So that is the model. So the election is conducted using the election algorithm is conducted using VRF execution, and the leader can, as a part of the proposal, can also present the proof of its election or is winning the election. So that's the model adopted. Ouroboros Preos, very similar model adopted in Algorand. Now, proof of stake model combined with BFT. So rather than going over all the systems, I'm just looking at some of the specific aspects like bond deposit. So Casper, Ethereum's Casper, it requires 32 ethers minimum. Algorand does not require any deposit, and there is no penalty model in Algorand. Casper has a penalty model. They call it the slashing model, and penalty model is important, essentially to detect misbehavior and penalize them. So other is election of the sub-stakeholders, how to conduct the election, a pseudo-random election conducted in the Algorand, and the model is very similar to what I just described, the verifiable random function based model. So only those who got elected, they either to the committee or as the leader, they can show the proof of their election. So it keeps the identity of the committee members or the leader, it keeps private. So essentially as a defense against the denial service attack. Most of the system will assign votes. The voting weight, the voting power will be proportional to their stake, done in Casper, done as Algorand, Tendermint. Okay. Then periodic reconfiguration of committee. Algorand does that. In fact, it goes to the extreme of reconfiguring on every round. It conducts this election using the verifiable random function on every round. Delegated proof of stake model, it is adopted in EOS. The stakeholders will essentially participate in election just like a social or political election and elect their representatives, and 21 of these representatives form the delegates, a committee of delegates, and these delegates essentially perform the job of or the task of proposing blocks and voting on the blocks and validating the blocks. It requires a Byzantine agreement model that at least 15 of the participating delegates must vote on acceptance of a block. Now, the criticism of this kind of model, it's somewhat centralized with only 21 producer nodes or delegates. And there's also concern of the effectiveness of the elections, social elections, where the stakeholders have to elect their representatives. The next, I'm going to briefly talk about the proof-of-elapsed time model. It was developed by Intel, and it requires a trusted execution environment, which is Intel's SGX, software guard extension. And the idea is very simple. A miner, rather than performing computation and wasting electric power, each miner goes to sleep for some random amount of time and presents a proof using the SGX attestation mechanism. It presents a proof the time it slept. And the one who sleeps for the shortest amount of time is considered elected the leader, and its block will be accepted in the system. So that is the model developed by Intel for the Hyperledger Sawtooth. By the way, Hyperledger Sawtooth, again based on the SGX model, also provides a BFT-based protocol, traditional consensus-based protocol, and it also has another model called POTS, which is POTS stands for Proof of T-Stake, combine trusted execution environment attestation along with stake, and conduct an election very much like Algorand kind of election. Next, I'm going to briefly talk about proof of authority model, which is suitable in permission blockchain systems. In proof of authority, which has been adopted and used in Ethereum's test networks, Coven and the Ring-B test networks, and it developed Aura and Clique. These are the two different proof of authority based models. And the notion is that in the consensus group, a trusted set of nodes with known trust levels or reputation, they are admitted in the group to perform the validation and the ordering of the blocks in the transaction. There's a paper which does the analysis of these two protocols, Aura and Clique. Aura is used in Coven, Clique is in the Ring-B testnet. And by D'Angelis paper, which performs an analysis, and what that analysis shows that Aura may fail to guarantee consistency, where Clique gives eventual consistency. One of the weaknesses of Aura protocol that it relies on synchrony of physical clocks, Unix clocks on the network. And if the clock gets off, if they are not synchronized correctly, then this may create issues in the correctness. Now, next I'm going to talk about next 3-4 minutes on the blockchain based on directed acyclic graph model. So essentially abandon the linear chain structure and adopt a directed acyclic graph structure of where the nodes in the directed acyclic graphs, they are either blocks or transactions. It's motivated that provide high concurrency and validation and faster confirmation. This model has been adopted in several systems. Close to about 20 different systems have been explored, and there's a very nice survey article you see here, reference at the bottom of this slide, and diving into DAG-based blockchain systems. Very nice, comprehensive survey. So there are two models where the DAG is maintaining. It's a transaction-based, where each node in the directed acyclic graph is a transaction, or it is a block-based. So IOTA Tangle, developed for Internet of Things, GraphChain, Hashgraph, Byteball, DAGcoin, these are all maintaining transaction-based DAG. In contrast, block-based DAGs, Spectre, Phantom, these were for some first system proposed based on directed acyclic graphs, Conflux, other system. So let's briefly look at the model. The general model is as follows. A new transaction in the system has to validate or approve at least one or more. And how many, that number depends on the specific system and the model. It has to validate, approve at least one or more transactions already in the DAG, directed acyclic graph structure. And there's also notion of indirect approval. When a new transaction approves a transaction in the DAG, it is also approving other transactions starting from that path all the way to the genesis. All the transaction, it is approving them. And it is essentially contributing some weight. There's notion of weight in the iota, so it's contributing weight to those transactions. So that is the notion of indirect approval. Now this model used in iota, it is used in complex and graph chain and many other systems. So the design issues are as follows. When a new transaction, which transaction should it select to validate? So the idea is that select tips. Tips are those transactions which have not been yet validated or approved. So I'm showing here in this diagram 2 tips. Okay, these have not been yet approved. A new transaction, pick one of these tips. There's also one important guideline or requirement that the DAG should grow as a band in one direction rather than as a random graph growing in all possible directions like a star structure. It should also, the rule should be such, it should prevent splitting of the DAG. So these are some of the driving requirements in the designs of these protocols. And finally, the consensus problem, how to detect conflict, how to determine the finality of transactions. And for that problem, the DAG maintains a partial order of transactions, which is chronologic, which also shows the chronological precedence of the order. For detecting and resolving conflicts, one need to have a total order. One need to define a total order for all the blocks or the transactions in the DAG. And based on the total order, then one can determine among the 2 conflicting transactions, that one which is appearing earlier in the order, that should be accepted, and others should be orphaned or rejected. Now, solution to the consensus problem, I just described to you the conventional traditional way. And so solution to the consensus problem tend to differ significantly across different systems. So one approach is which I just described, adopted in Conflux and Spectre. And what they do is identify a pivot or a main chain in the system, in the DAG. In the directed acyclic graph, identify a path, call it a main chain or pivot, and around that pivot chain, they would have a sorting algorithm to determine a total order of all the transactions in the block and detect conflict and resolve conflict. IOTA Tangle has a very different model, and it's a probabilistic model. So if there are 2 transactions conflicting, then pick the transaction which has the highest number of indirect approvals. And that transaction is a higher confidence level or confirmation level. So it's a probabilistic model. And IOTA Tangle is very interesting design. There also a random walk model, how to select randomly some tips and conduct this kind of an analysis or confirmation. There's a very interesting model. The number 3rd is based on the gossip protocol, which is the hash graph Hedera, used in the hash graph Hedera system. It's a very interesting model. It's based on gossiping. It maintains a graph of transactions and which is capturing the precedence order happened before relationship. It's maintaining that graph, is maintaining that. The graph structure in its addition and its through a gossip protocol, the information is disseminated in the network. Hash graph, Hedera hash graph is a permission system. There's a fixed number of participants participating in it. It can tolerate up to 1/3 of malicious or faulty participants. And based on this gossiping information, which is continuously and periodically exchanged, each participant maintains its structure of the hash graph. And with that structure, there's an information which essentially indicates which transactions have been seen by other participants in the system. And these are called the witnesses. If more than 2/3 have seen a particular transaction, those become the famous witnesses. And there's a virtual voting protocol integrated in the system. It's not, the details you can find in the Hedera hashgraph papers. So the conclusion, Bitcoin's proof of work model provides a probabilistic model for consensus and finality. It also provides Sybil resistance. It has a large energy footprint and low transaction throughput, high confirmation time. All these have motivated exploration of many other models. BFT, classical consensus protocol. They provide deterministic finality, high throughput, low latency. Group size is limited, and it requires some kind of admission control, view change protocol based admission control. These are easily applicable in permission system, and indeed Hyperledger and family of those Hyperledger platforms have done that. However, using BFT and permissionless system, it's a challenging problem, and still it's going to remain an open challenging problem in the coming years. Proof of stake has emerged as an important and significant alternative to proof of work. In fact, if you look at the Ethereum's, their future plans essentially to move away from proof of work and essentially make everything based on proof of stake. There's a long-range plan. Such protocols require election protocols, periodic reconfiguration of committees for BFT protocol execution, and one important thing, that models for bond deposits and slashing penalty model. These are necessary. Directed acyclic graphs I just described, and these have gained attention in some application domain environments such as Internet of Things. It presents a unique model and interesting model, and further research is still needed in this area. Finally, new designs are frequently proposed, and word of caution here, they all require careful evaluation. A lot of designs are proposed, sometimes they may be ad hoc, and they require very careful analysis and evaluation. I would like to then point out now here, there are many useful references. You can find in-depth information on things which I just discussed in my presentation. Number one, the survey of consensus protocol appeared. This is the most recent survey. It's a very comprehensive and detailed survey. I would encourage you to look at it. Then the number two, these are also very detailed, nice, comprehensive survey. And they're from 2017, and they are still relevant today. Number 4 and number 5 are survey articles and broad topic of Bitcoin, cryptocurrencies, and the blockchain system. With this, now it's time. I have taken much longer than we had planned. I had time for questions, and thank you for your attendance here. And here is my contact information. Back to you, Kerry.
All right, very good. Thank you. This was a great presentation, and you can tell by all of the questions we've gotten. So let me go to the first question here. This came early in the discussion. It said, what is the average cost of the energy expended in a Bitcoin transaction?
Average cost of energy. Okay, these estimated, there have been several estimates of that energy. I just computed one and based on that snapshot on June 7th, but you're looking at, let's pick a number, okay? So for 400 to 500 kilowatt of energy. That's the kind of energy a typical transaction is consuming today. So it's a very high energy footprint there.
Okay. The next one is, when developing a new consensus mechanism for blockchain, what would you consider as the most important goals for the consensus to achieve? What would be the most effective manner in which to test the effectiveness of the new consensus?
Okay, there are several measures involved, okay, and there has been quite a significant number of developments. So first consensus protocol in the Byzantine was PBFT by Castro and Liskov. After that, even prior to blockchain systems, number of other protocols were proposed, reducing the complexity, reducing the message complexity, because PBFT, Practical Byzantine Fault Tolerance Protocol by Castro and Liskov, that required order of n square complexity, and view change protocol required order of n cube complexity. There have been several developments which have reduced this. For example, I'll mention hot stuff. So message complexity is one thing. Other is latency. Okay, how long does it take? Okay, then of course, all these consensus protocol will guarantee confirmation. That is, the consensus is final. So the finality is guaranteed by the traditional consensus protocol as compared to the proof of work protocol. So the performance in terms of message complexity and the latency, those becomes the most important factors to consider in the designs.
Okay, the next question is, could you please comment on the relationship between goals and consensus protocols? E.g., proof of importance can be used by hiring agencies to reliably select candidates based on their reputation. Candidates' reputation is a scarce source, so it can be used in POI consensus.
Certainly reputation kind of based models that can be employed, can be utilized here. But if somebody, it's malicious behavior, of course, their reputation will be tarnished and they will pay for it in penalty in a different kind of way. So the penalty in a different way, what they're staking is their reputation. So indeed, these kind of models, several other such models have been around and have been kind of pursued in this. If you look at the proof of authority, is very much along those lines. It's a reputation model, trust level reputation, which the participants have acquired in the system with their past behavior. So yes, those can be utilized in the system and have been utilized in explorations. So the directions, there are many open directions in this regard.
Very good. The next person asks, what is the issue of blockchain scalability with respect to consensus protocol?
No, this blockchain scalability. Now, if you're looking at scalability, there are two different options, aspects of it. One is the size of the network. Okay, that's one aspect of scalability. Other is the scalability in terms of throughput of the transactions. So, could you just repeat that question again for me?
Absolutely. It says, what is the issue of blockchain scalability with respect to consensus protocol?
Right. Okay. So the consensus protocols, the scalability of consensus protocol in terms of their communication complexity. If you look at the proof of work, it is order of n kind of protocol. It is highly scalable, going up to 10,000 nodes. But the cost we are paying in terms of latency, confirmation latency, that is the high cost, okay? The cost is again in terms of very low throughput. So what is needed in the consensus protocol? The protocols which can essentially have a large network size, but still they can guarantee, ideally the protocols or ideal protocols are those which can essentially work in large network size, but they can also guarantee low latency in confirmation time and high transaction throughput. So those would be the guidelines and the goals for the consensus protocols to achieve. So both the scalability aspect in terms of the size of the network as well as in terms of the performance scalability are needed.
Okay, that's great. What evaluation needs to be conducted on a new consensus mechanism to ensure that it is secure and efficient enough for public use?
Okay, that's an interesting question and I must say, it's also a difficult question. So security analysis is not it requires experts to look at it carefully, okay? All kinds of attack vectors has to be properly examined. And this reason, as I was mentioning earlier, the many proposals arise and they have to be looked at by the community. Sometimes it is an attack scenario may be missed by one, but this reason the open source, something which is published openly and being examined, those are the kind of methods that scrutiny by a big, broad community of experts that is needed. And the attack vectors may be very different. They may be very specific specific to a design, or they may be very general. For example, a Sybil attack kind of thing. Sybil identity may be general, but there may be very specific attacks which may happen. So, as I mentioned, yes, the question is hard. There is no specific solution that one can prescribe, but it does require security analysis with proper expertise and careful thinking by also just not a small group, but a broader group of experts.
Okay, very good. I know we've got a lot more questions here, but maybe we'll take a couple more,
Sure.
given that we've gone a bit over time. So this next question is proof of stake any more or less vulnerable to quantum attacks compared to proof of work?
Quantum attack, we're talking about quantum computing, right? So is that what I believe is mentioning? So yeah, I think, yeah, but anything, if we're talking about quantum attack, then anything which is based on cryptography is going to rest on cryptography. Then we are talking about that, can the crypto keys can be broken with any quantum attack? If that's what the question is intending, that anything which is making use of cryptography, and many of these stake-based protocols, for example, Algorand, etc., conducting random function kind of election, then these are going to be vulnerable. So such attacks, because the election is conducted using pseudo-random algorithms. So indeed, they are exposed to those kind of attacks if the keys can get compromised.
Okay, very good. We'll make this one our last question, and this one touches on 5G. So which type of blockchain is appropriate for 5G networks? Which consensus protocol will be considered more suitable for 5G networks?
Okay, this is one question I'll have to plead my ignorance. So I'll have to plead, no, I cannot really will be able to, say that which one would be the...
Maybe we'll skip over to the next one and then end on this one. With all of the challenges of consensus models, why do we want to continue to look for a solution versus use trusted third parties like central banks?
The whole notion of this technology, starting from Bitcoin, to not to have a trust in any third party. Sure, we indeed, in real life, we have to put our trust in many other institutions and organizations one can do, but then we are essentially going back to the same conventional old way of doing things, but it is a completely different paradigms where there is no trusted third party involved. So essentially, basically the question saying just rely on our conventional, traditional, classical way of putting trust in certain institutions. So that has been done, and it can continue. We can certainly continue, but these other models, they would be adopted and explored in where environments there cannot be any trusted third party in the system. So certainly those are applicable where there is no trusted third party can possibly exist.
All right, very good for the answer. Thank you very much, Dr. Tripathi, for your presentation. I'd also like to thank all of you for attending. Our upcoming webinar for the month of June is Making Conflict Work. That's going to be in our Build Your Career webinars. That'll be on the 22nd of June. And in July, we have the following webinars, quite a few actually. Environment Modeling-Based Requirements Engineering on the 15th of July. Overview of IEEE Smart Manufacturing Standards. That's part of our standards webinar series. And that'll be on the 20th of July. Poor Productivity Habits and How to Kill Them. That'll be on the 22nd of July. Again, that's the Build Your Career. And then we have one actually in Spanish coming up, Sistemas Inteligentes, Frugales y Ciberfísicos, Diseños y Implementación. And that's on the 29th of July. Registration for these is now open, and we will be sending you a link to these future events along with the recording of this webinar. Again, Dr. Tripathi, thank you very much for your presentation. It was great.
And once again, thank you very much for inviting me, and thanks to all the participants and attendees today. Thank you very much. Bye-bye.
All right. Everybody have a great day.